It is my pleasure to introduce Professor Frances Kirwan at Oxford University. The title of her talk today is Variation of Non-Reductive Geometric Invariant Theory.
So, very many thanks. It's a great honor to be here as part of the 50th anniversary conference for JDG, and it's a particular pleasure for me to be back at Harvard. It's not 50 years since I belonged to this department, but it's well over 30 years, so it's very nice to have an excuse to be back here. So my title is Variation of Non-Reductive Geometric Invariant Theory, but I'm going to leave the variation bit to the very end. So I really want to spend nearly all my time talking about motivation for and what the issues are in trying to extend classical geometric invariant theory, GIT, to a non-reductive setting for when we've got linear actions of non-reductive groups. So just to start with, very generally setting the scene. Of course, in algebraic geometry, moduli spaces, moduli stacks typically can be constructed as quotients of schemes or varieties by linear algebraic group actions. And any linear algebraic group, has a unipotent radical. It's a unipotent subgroup, maximal normal unipotent subgroup, with the quotient being a reductive group. If we're over C, at least, we can describe it as a semi-direct product. And many of the groups that appear when you're in classical moduli spaces, moduli problems, are actually reductive groups, but not all of them. And if you're wanting to quotient by a reductive group, then you can try and construct quotients and study them using Mumford's classical GIT. And so typically the sort of groups that are coming up are general linear groups, special linear groups, on products of those, all reductive, automorphism group of a projective space, PGL, certainly reductive. But then there are also interesting automorphism groups, so for example of weighted projective spaces that are not in general reductive, so simple example of this weighted projective plane. So part of the motivation for studying quotients by non-reductive groups is that it actually comes up even in the very classical moduli problems, such as the really classical one of curves, projective curves. If you're interested not just in the stable things that GIT typically gives you a nice quotient, a nice moduli space, but also you might be interested in unstable objects for your whatever problem you're thinking about. So the classical example, the most well-studied example, I guess, is moduli space of stable curves. And so a curve is stable if it's got, it's allowed to have some singularities, but fairly minor singularities. Actually, let's make this slightly more interesting. So we're allowed to have nodes, but the automorphism group, at most, the singularities are at most nodes, but the automorphism group has got to be finite. So if you've got a P1 in there, then you've got to have at least 3 special points, singular points, to make the automorphism group stable. So that's a moduli space that's very well studied, very well understood, and it can be constructed using classical geometric invariant theory by looking, for example, at K for sufficiently large integer K. You look at K canonically embedded curves in a projective space, and you look at the Hilbert scheme, and then you quotient by SLR plus 1. So, so that's a beautiful construction. There are some subtleties involved, but it gives you a beautiful construction of a projective moduli space. And you can ask, well, what about if you were interested in unstable curves and singular curves? So, of course, singular curves have been studied for a long, long time as well. And I think probably in the 1950s maybe, there's a nice description of singular curves. This is projective singular curves in terms of the normalization or the resolution of singularities. So topologically, you can describe the singular curve just in terms of a simple equivalence relation on the normalization, just which points get glued together in the singular curve. And then you need some algebraic data as well to describe the singular curve as an algebraic curve. So if we, so back in, I think, the 1960s, EB used this construction to try and classify maybe the simplest sort of singularities, so unibranch singularities where the normalization map is actually bijective. And his construction, so he ended up using slices rather than a quotient for a certain non-reductive linear algebraic group action. And in a sense, what he should have been doing was taking quotient by this non-reductive linear algebraic group action, but there wasn't a theory to allow him to do that. And the group that came up in his construction is sort of a reparameterization group, a group of jets of germs of biholomorphisms of C at the origin. And it's a group that's come up in lots of other places in more recent decades, for example, in studying jet differentials. And you can describe it as a group of matrices in this upper triangular form. So the entries along the top row of the matrix are essentially free parameters. The first one, A1, has got to be non-zero, and the others can be any complex number. And then the terms that I haven't put in above the diagonal are polynomials in these parameters. So it's a semi-direct product of its unipotent radical, which is the strictly upper triangular ones, where A1 is 1, by C star, the multiplicative group. So this is non-reductive group action. Okay, so from EB's point of view, non-reductive group actions were coming in if you in trying to study and classify singular curves. And also, if you go back to the construction of MG bar, the moduli space of stable curves of genus G, as a GIT quotient by the reductive group SLR plus 1, it turns out that construction suggests another sort of way that one would want to use non-reductive GIT rather than classical GIT to study the unstable things. Similarly, if you go to other classical moduli spaces, such as sheaves of over a fixed non-singular projective scheme, then you can talk about sheaves of fixed Harder-Narasimhan type and try and which will be unstable for all except for the trivial Harder-Narasimhan types, and you can think about trying to construct quotient spaces of those. And again, it turns out that what you want to quotient by is really a parabolic subgroup of the reductive group that you started with. Because, so there's theory from classical GIT for reductive groups, which tells you that if you've got a reductive group acting linearly on some projective variety, as in the case for the construction of moduli spaces of curves, where you've got SL acting on this projective scheme K, then you always get a stratification of that, scheme, indexed by, it turns out, by a finite subset of a positive Weyl chamber for the, well, maximal compact subgroup, SUR+1 in this case, which has the semi-stable points as the open stratum, and then decompose into other strata. And each of these unstable strata can be expressed in terms of a certain parabolic subgroup of the reductive group that you started with. And it described sort of inductively and in terms of semi-stability in the classical sense, but for the action of the Levy subgroup, the reductive bit of the parabolic, with respect to a linearization that's been twisted by a certain character of the parabolic group. So I'll be saying a bit more in detail about this in a minute, but roughly speaking, it tells us that if we want to construct a quotient of one of the unstable strata, or at least an open subset of one of the unstable strata, by the original reductive group G, it comes down to looking at the linear action on a projective subvariety of a parabolic subgroup, but with the linearization twisted by an appropriate character. So we're getting non-reductive groups coming in, even if we start off with a reductive setting. So I just want to, at this point, remind you briefly, or tell you, about the classical version of GIT, geometric invariant theory, which Mumford developed in the 1960s. So let's assume that we've got a reductive group. Let's say that we're working over the complex numbers for simplicity. And we've got a complex projective variety acted on by the reductive group, and we need a linearization of the action, so an ample line bundle and a lift of the action to the ample line bundle, and we can think of the variety as embedded in projective space and the action given by a representation. And then the idea is that to the projective variety, well, with the line bundle, the ample line bundle, you can look at the homogeneous coordinate ring, or the algebra of sections of powers of the line bundle. And the linearization tells you that the group, you get an induced action of the group on that. So you look at the algebra of invariance, and then if you've got a reductive group action, that algebra of invariance is itself a finitely generated graded complex algebra, and corresponds therefore to a projective variety, which we think of as the GIT quotient. And the inclusion of the invariance in the full algebra gives us a rational map in the other direction. So, so we get the rational map from X to the GIT quotient. And so we can study the geometry of the GIT quotient using this rational map. So it restricts to a morphism, so it's not always well defined everywhere, because you may have points in X where there are no invariants that don't vanish at X. But if you restrict to the so-called semi-stable points, you get an open subset where the morphism is well defined. And it turns out, it's not at all obvious, but it turns out that the restriction is actually a surjective morphism onto the GIT quotient. So, and then you can restrict further to the stable points where you really do have a nice geometric quotient, whereas the semi-stable points, typically you have orbits that get identified in different orbits that get identified. So topologically, you can think of this GIT quotient as the semi-stable points modulo this equivalence relation, often called S equivalence, where two semi-stable points are equivalent if and only if the closures of their orbits meet in the semi-stable set. And you can also describe the GIT quotient in terms of moment maps and symplectic geometry. So one of the reasons that classical GIT is really powerful is that there are, you can describe which points are semi-stable and which points are stable without having to know what the G invariants are. So the invariants in general are very hard to understand, but we have these Hilbert-Mumford criteria which tell us relatively explicitly in terms of combinatorics and the weights and so on when points are stable and semi-stable. So that's very powerful. And so something else we can do in the classical setup is construct what's in some sense a partial desingularization of the GIT quotient. So even if x is non-singular, if you've got semi-stable points that are not stable, then you're collapsing lots of different orbits, and typically you're introducing singularities to the quotient. Whereas if semi-stability coincides with stability, then at least for a non-singular x, you get an orbifold. So in general, at least if you've got some stable points, you can do a sequence, sort of canonical sequence of blow-ups, which get you from your original space x to a new space x tilde, which does have, where you haven't modified the stable points of x at all, and you end up with the situation that semi-stability does equal stability in the blown-up space. So you can think of this as giving you, in some sense, a different projective completion of the quotient of the stable set, which is less singular. You've essentially got rid of the singularities caused by the group action. So summarizing, at least summarizing the bits of the picture that I want to go on and generalize in a non-reductive setting in a minute, we have, in the classical GIT case, we have the best case, which is when semi-stability is the same as stability, and when you've got some stable points. Then you've got a geometric quotient of the stable points, which is itself a projective variety, and it's this GIT quotient. And more generally, at least if you've got some stable points, then you can, you've got the geometric quotient of the stable points, and you can sit that as an open subset inside a projective variety, which is itself a geometric quotient of this blown up, the stable things in this blown up space. So that's the classical, the reductive situation. And so we can ask what happens if the group is not reductive. So then you run into issues right at the beginning of the construction, because then the algebra of invariance, the graded algebra given by the invariance, is not necessarily finitely generated. And so although you can define some sort of projective scheme, it's not very well behaved. And if we want to get something more explicit and something that really will be a variety, then we're in trouble. So it turns out that defining stability and defining an open subset of stable points you can define semi-stable points as well. You get a nice geometric quotient of the stable points, and you get something that sort of maybe corresponds to a GIT quotient of the semi-stable points. But three things, important things from classical GIT go wrong in general. So this enveloping quotient is not necessarily projective. The morphism from the semi-stable points to the enveloping quotient is not necessarily onto. And you can't even sort of combine those two problems into one, because the image of the semi-stable points in the enveloping quotient is not even necessarily a subvariety, and it's just a constructible subset. And also, there's no obvious way to generalize the Hilbert-Mumford criteria. So it's not, in general, particularly easy to work out which points are semi-stable and unstable without having to go via understanding what the invariants are, which is a very hard problem. However, it turns out that if, for a large family of non-reductive groups, which include parabolic subgroups of reductive groups, then you can make things, make geometric invariant theory work nearly as nicely as in the classical case, provided that you're willing to, well, first replace the line bundle by a sufficiently large tensor power of itself, so that's not an issue in GIT, that doesn't affect things, but then also to twist the action by a suitable character. So this is the setup where we've got a unipotent group, or the unipotent radical of the group that we're interested in, which is what we're calling graded unipotent. So we want to know that there's a one-parameter group of automorphisms of this unipotent group with all the weights of the induced action on the Lie algebra, all strictly positive. So if you've got an upper triangular a group of matrices and a diagonal C star which normalizes it, then that will certainly be the case. And so then if you look at this semi-direct product of your unipotent group with the one-parameter group of automorphisms which grades it, then you've got a non-reductive group. If you've got a linear action of this U hat, this semi-direct product, on a projective variety, then it turns out that if you're prepared to twist the action by a suitable rational character, then GIT works more or less, well, not quite as well, but almost as well as in the classical case. So there are two parts to this. So the nicest case is where this condition star is satisfied, and so it's slightly technical condition, but roughly speaking, we should think of that condition as saying that semi-stability equals stability for the unipotent group action. And, well, actually, I think that's if you use Mumford's original definition of stability, whereas what we now normally talk of as stability is what Mumford called properly stable, and then you would need a zero for that dimension in condition star. But so roughly speaking, star is saying that stability corresponds with semi-stability for the unipotent action. And in that case, if we look at the action of U hat, the semi-direct product with the one-parameter subgroup, then we do get the algebra of invariants being finitely generated. That means we get a projective non-reductive GIT quotient associated to the algebra of invariants, and that is just a nice geometric quotient of the semi-stable set, which is the same as the stable set, by the U hat action. And you have a nice, very simple Hilbert-Mumford description for the semi-stable points, which are the same as the stable points. So that's the really good case. And even without the condition that semi-stability coincides with stability, you can still do some blow-ups. So you can construct a U hat equivariant blow-up of your original X without affecting the stable points, so that you get a nice projective completion of the stable points, if you've got some stable points. So that applies in particular, if we go back to the situation that I described before, when you've got a reductive group action, linear action of a reductive group on a projective variety. So we have this stratification that I described before, which is actually, we can think of as the Morse stratification for the norm squared of the moment map, if you want to have a moment map picture of what's going on. And so again, we've got these strata and the unstable strata trying to quotient an unstable stratum by a parabolic, by the group action corresponds to trying to quotient a projective subvariety by a parabolic group. And this parabolic group always has the situation that its unipotent radical will be graded by a central one-parameter subgroup of the Levy subgroup, the reductive part. So that means that if we want to quotient by the parabolic, provided that we have an appropriate twisting, then we can quotient first by the U hat, which is the unipotent radical, together with this central one-parameter subgroup of the Levy. And then we can quotient by the residual action of the Levy quotiented by its central subgroup, which is reductive. So, and that sort of situation works whenever you've got something like the parabolic, which has is a semi-direct product of its unipotent radical by a reductive group, if that reductive group contains a central one-parameter subgroup which grades the unipotent group. So, so we can go back, for example, to what I was talking about, the moduli spaces of sort of unstable objects that I was talking about before. So, for example, if you're interested in looking at sheaves of fixed Harder-Narasimhan type over some fixed non-singular projective variety, then there is a very well-known construction back in the early 90s, I think, by Carlos Simpson, of the moduli space of semi-stable pure sheaves on this non-singular projective variety W with fixed Hilbert polynomial as a GIT quotient by a linear action of a special linear group on a scheme which is closely related to a quat scheme and G equivariantly embedded in a projective space. So you can set up this, this construction so that if you're interested in sheaves of fixed Harder-Narasimhan type, then they form a stratum in the stratification of this, this Q as I was just describing. And so then you can use the non-reductive GIT to try and, for the associated parabolic, to try and construct moduli spaces of sheaves of this fixed Harder-Narasimhan type by doing this non-reductive GIT. So you can also look at moduli spaces not just of sheaves, but of complexes of sheaves. And that's going to be more relevant when I finally say a little bit at the end about variation of GIT, because there's an interesting variation of GIT going on there. So also, if we go back to our moduli of curves, then you can try and think about, again, using non-reductive GIT for associated parabolics in the setup that I described right at the beginning. So if you've got this thing that I call K sitting in the Hilbert scheme for little k canonically embedded curves in a projective space. So, so my one of my students, Josh Jackson, is looking at all the details of this for his thesis. So the idea is that you want to, first of all, work out what, so in this case, it's not so clear as in the sheaves case how to parameterize these unstable strata and what the sort of type of the unstable curves should be that corresponds to the different strata that come in. And it sort of links in with the Serre-Rosenli construction of singularities that I talked about before. So that's a particularly nice case to try and apply the non-reductive GIT to it, because the condition that semi-stability coincides with stability for the unipotent radical sort of is automatically satisfied for these this moduli space of curves construction, though there are also subtleties in that GIT picture as well. And also whereas for the Harder-Narrow-Siemann, for the sheaves or complexes of sheaves of fixed Harder-Narrow-Siemann type, that's certainly not the case. So you expect to have to do lots of these blow-ups before you get a nice quotient, which you don't have to do for curves. And also for curves, there's no particular need to worry about variation of GIT, as I said. So for curves and for sheaves, but for if you're interested in complexes of sheaves and possible links with derived categories and so on, then the variation does come in. So maybe I will just say a little bit now about classical variation of GIT. So if you've got a reductive group acting linearly on a projective variety, then without changing the actual action of the group, you can think about how you can change the linearization. So, and what effect that might have on the quotient. So if you you can potentially change the line bundle, the ample line bundle, and then if your group is not semi-simple, you can also, if you've got a linearization, you can change the linearization by shifting it by a character of the group, and that won't affect the actual action on the underlying projective variety, but just on the line bundle. And so, so you can study how the quotient, the GIT quotient varies in this setup. And very roughly speaking, you have a sort of a convex picture of where you've basically got some sort of convex subset of a rational vector space, essentially, and you're dividing it up into convex pieces. And you have that if your linearization sits inside the interior of one of these chambers, then you expect that, well, if you're lucky, semi-stability coincides with stability in the interior. You have a nice, well-behaved GIT quotient, and it doesn't change in this as you move around in this chamber. But then, if you cross one of the walls from one chamber to another, then the GIT quotient will change in a way that you can sort of describe. So that's the classical setup, and so we can think about what happens for in the non-reductive setup that I was talking about. So if we assume that we've got a linear algebraic group with a unipotent radical U and Levy subgroup R, so that it's a semi-direct product of the unipotent radical and this reductive group R, and assume that it's acting linearly on a complex projective variety with respect to an ample line bundle, And we have to assume that this reductive, the Levy subgroup, contains a central one-parameter subgroup which grades the unipotent radicals so that all the weights of the action on the Lie algebra of the unipotent radical are strictly positive. So that will happen, as I said before, if you've got a parabolic subgroup in a reductive group. That's always the case. If you've got the automorphism group of any complete toric variety, it always has this structure. There are lots and lots of examples of non-reductive groups with this structure. And of course, a reductive group fits into this picture as well, where the unipotent radical is just trivial. So in this situation, we've got a bit more that we can think about varying. So we're not just varying the line bundle and the lift of the action of the group H on X to the line bundle, so the linearization. Of course, we've got some constraints on the linearization because we have to be prepared to twist by this character of the central one-parameter subgroup appropriately. And, oh yes, I think I've just realized that I didn't really describe what that twisting was. So, so the twisting is such that you look at the weights of the one-parameter subgroup acting on the projective variety, and you have to twist so that so twisting by a character just basically moves the origin, translates the origin in this line, and you have to translate so that the origin just lies just a little bit above the minimal weight. So that's the twisting that gives you a nice GIT quotient. And yes, so there's a little bit of subtlety here. So if all you're interested in is what the semi-stable points, stable points are, then you can twist so that the origin lies anywhere in this sort of lowest bounded chamber, if you like. So below here, you'll get in your variation of GIT picture, you'll get an empty quotient. Above here, you'll get an empty quotient. And then you'll have these bounded chambers where you'll hope to have a non-empty quotient. And if you're just interested in what the semi-stable points are and what the stable points are, then it doesn't matter where 0 is in this minimal bounded chamber. But if you want to actually know that the invariants are finitely generated and that you get an induced line bundle on the quotient, induced ample line bundle on the quotient, and so on, then the argument is an inductive one, and it seems that you have to be prepared to be sort of just a little bit above the minimal weight. So yes, so in the non-reductive setting, we can vary the linearization, but we have to have this constraint on twisting for by a character of the central one-parameter subgroup which grades. But also, of course, we can vary the central one-parameter subgroup. So we have to think about the possibility of these two different things varying. And the simple case is when the condition star that I had was satisfied. So that's basically saying that semi-stability coincides with stability for the unipotent radical. So that's the nicest setup. In the general case, we can actually sort of do a blow-up of X to make sure that star is satisfied sort of whatever choice of linearization you've got, so that you can reduce to the simple case when semi-stability does coincide with stability for the unipotent radical. So so we get a picture which is sort of similar to the GIT, the classical GIT picture, but has some differences. So we can, if we want to vary the, if we fix the central one-parameter subgroup and we just vary the line bundle and the lift of the, and the linearization, then essentially we have the same theory as in the classical case, and we can understand what's going on there. But the sort of more the new situation is the possibility of varying this central one-parameter subgroup. So what you have to look at is the center of the Levy subgroup, which I call Z, and so we can look at the weights of the action of this this center, this nice torus on our projective variety, and we can also look effectively in the, so these are lying in the dual of the Lie algebra of the center, and then in the Lie algebra itself we've got some sort of some rational cone, or it's the interior of some rational cone corresponding to all the one-parameter subgroups which do actually grade the unipotent radicals, so which act on the Lie algebra with of the unipotent radical with strictly positive weights. So what we're sort of looking at is the convex hull of this set of weights, and then there's just part of the boundary of this convex hull which will correspond to the parts of the boundary which would correspond to being the minimal weight for some one-parameter subgroup in this cone. So yes, I haven't drawn this very carefully, but my guess would be that in this picture it would be something like those two pieces, bits of the boundary would correspond to where you would have the minimal weight for some particular one-parameter subgroup. So, so in order to have a well-behaved GIT quotient by this non-reductive group, what you have to do is twist the linearization by a rational weight which is supposed to be in the interior of this polygon, but very close to the allowable part of the boundary, and then it will have this property of twisting for the one-parameter subgroup that you've chosen. So we don't really have exactly the same sort of picture of convex chambers, but in this polygon we're only allowed to look at what happens relatively near to this piece of the boundary. But other than that, the picture is very similar to the classical GIT, because if you want to move around close to the boundary of this convex polytope, so in the picture up there, I think the red part is supposed to be the allowable part of the boundary, and the blue dotted lines are supposed to be giving you the the idea is that I'm using the standard inner product on R2 to identify the Lie algebra with its dual, and so the dotted blue lines are the boundary of the rational cone corresponding to the one-parameter subgroups that grade the unipotent radical. So if we move around the interior of the convex polygon, the polytope, just inside the allowable bit of the boundary, then it turns out that you can achieve that. It's not too difficult to see, actually, that you can achieve that with finitely many steps, for each of which you can choose the central one-parameter subgroup, which grades the unipotent radical to be fixed. So if you're if you want to be close to a codimension 1 face, then basically you've got no choice about what the one-parameter subgroup is. But if you're at, well, in this two-dimensional picture, if you're at one of the vertices, or up here, if you're at this vertex, then you've got quite a lot of choice for which which one-parameter subgroup will make that vertex the minimum. So we can move around with these finitely many steps, such that for each step we can choose the central one-parameter subgroup to be fixed. And then you can also prove that when you regard the central one-parameter subgroup grading the unipotent radical as being fixed, then varying the line bundle and the linearization under the constraints that we have to put on the linearization, it behaves just exactly as in the classical case studied by Thaddeus and Dolgochev and Hu. So you get this generalization of the classical variation of GIT picture with this slight extra ingredient from varying the one-parameter subgroup. Okay, so I think that was my last slide. Yes, it was. So I will stop there and thank you for your attention. So, yes, so what I've been talking about today for simplicity is the sort of internal situation where you want to study the invariance or a quotient for a group which already has this central one-parameter subgroup, which is of the Levy subgroup, which grades the unipotent radical. So you can also think of a sort of external situation where you what you're really interested in is, I mean, you might want to just be able to quotient by or look for invariance for the unipotent radical itself, rather than the U hat. So we had so to get a nice result, we had to look at the semi-direct product of the unipotent radical with a central one-parameter subgroup. I guess I was using C star. And so for the invariance of this, or if you've got this sitting inside some group H with U as its unipotent radical, these invariants will always be finitely generated, provided that you do this twisting of the linearization. So, but if you've got a linearization which isn't twisted appropriately, then we just don't know. And certainly there will be cases where you don't get finitely generated invariants. On the other hand, if you were just interested, as in the jet differentials case, if you were really just interested in the unipotent group, or slightly more generally, if you had an H which didn't have itself a central, the Levy subgroup didn't have a central one-parameter subgroup grading the unipotent radical, you might have a situation where there was a C star, so where your linear action extended to an action of a semi-direct product of H with the C star, where the C star did grade the unipotent radical and also commuted with the, the induced action on the quotient by the unipotent radical was trivial, so that effectively it was centralizing a Levy subgroup. So in that situation, you can say, okay, well, I know how to get a non-reductive GIT, nice non-reductive GIT quotient of this extension. Let's call it H hat. But what I'm really interested in is H. So in that situation, one thing that you can do is you can say, well, suppose I've got my action on X. Well, then I can look at the product of X cross, say, P1, and I can try and then if my action of H on X extends to an action of H hat, I can make H hat act on this product where it acts in the given way on X, and H itself acts trivially on P1, but the C star acts in the standard way. And I can try and take a quotient of this product by H hat. And that will, and I twist the linearization appropriately. I weight the P1 factor very heavily. And then what I get is in some sense, a stable set for the H action on X with a geometric quotient, which will definitely not be projective, but I'll be able to find a projective completion, which is the quotient of this product by H hat. So there'll be some sort of boundary stuff which comes from when I've got points in, well, basically I've got the origin in P1 rather than the C star in P1. So, so that gives me a situation where even in the sort of famous Nagata counterexamples where you know, where you've got a unipotent group acting and you know the invariants are not finitely generated, even in that situation, the action extends to a U hat. And so you can construct some sort of GIT quotient in the way that I've described. And what you're doing is you're saying that the grading and the extension by this C star is picking out for you a particular finitely generated subalgebra of the U invariants or the H invariants. So, which is then giving you a nice projective variety. So I think that so in the jet differentials setup, what's happening is that you're not getting all the invariants for the unipotent group, but you're getting a natural finitely generated subalgebra. And I think it does fit in nicely with stuff that people have already looked at, you and many others, in that situation. So yeah, maybe we can talk some more about it just later. But yeah. So there was one over there, but maybe I can answer it separately.